Day 152, Honors Physics, Electricity and Magnetism, homework problem number 24. Here we have two wires. Let's say they're laying on this paper on a tabletop. They're parallel to each other. They're 10 centimeters apart. We're not asking for the force that they're exerting on each other, because they will exert a force on each other that will cause them to attract. They're not asking for that here. They're asking for the magnitude of the net magnetic field at a point midway between the two wires. So they're asking about, say, this location right here, which is 10 centimeters from, no, 5 centimeters from each wire, because the wires are 10 centimeters apart. Let me label that 10 centimeters. All right, so each wire is creating a magnetic field that is hitting that location. So you ignore each wire, do one at a time. The equation is the magnetic field generated by a single wire is B equals mu 0 over 2 pi times the current in that particular wire divided by the distance you are from that wire. So you're going to do two calculations here. You're going to do B, I'll call this B10 for the 10 amp wire. You simply plug everything in with a current of 10 and a distance of 5. Well, let's just check before we do that. Well, I'll do that. It's mu 0 over 2 pi. The current is 10 amps, and the distance is 0.05 meters. And you can do the math there. B10 will be some number. All right. Well, let's look at direction for a second. So if I were to draw using a right-hand rule the magnetic field surrounding that wire, that means that I'll go down low first. The magnetic field is into the page here and out of the page there, going around, the magnetic field going around that wire. So what I care about is this. So that's what I'm going to draw at my location of interest. That is right here where the X is. I'll actually just put a circle around it. That represents magnetic field going into the page due to the 10 amp wire. Everything to the right of the 10 amp wire is into the page in the plane of the paper. At the same time, or going back over here far to the far right, I could figure out B15 by just changing only the current, the 10 amps, change the 10 amps to a 15, get a B15. It'll be slightly larger than the B field for the 10. And I'll use black for this one. For that wire, looking at the bottom, once again, the magnetic field, if I were to draw it, would be into the page there, out of the page there, towards the ceiling, as it goes around that wire. So bottom line, and I'll sort of superimpose these, if I go back up to our location of interest, the 15 amp wire will have a slightly stronger magnetic field that's towards the ceiling. I'll just give you an example. So say if that magnetic field strength for the 15 amp wire was, say, 25 Teslas, and for the blue wire it was, or the blue X is 20 Teslas, it'll be slightly smaller due to the 10 amp wire. The 20 Teslas is down towards the floor, the 25 Teslas is up towards the ceiling, so the net would be 5 Teslas towards the ceiling. So that would be the answer. You just have to calculate those two numbers and subtract them because they're going in opposite directions. If you reverse one of the currents, then those would be additive and you get 45 Teslas. But here's a tougher question. Part B. Is the magnetic field 0 at some point on the line joining the two wires? And the answer is yes. Part B is a little bit tougher. I'm going to start a new page here. So in Part B, they're asking if there's a location on this line, a line that is perpendicular to the two wires, joining the two wires, or just indicating this space between the two wires. There is a location on there, and the location is closer to the 10 amp wire. They're asking about this location, right about in here. I'll mark it with a red dot. I can put an X or whatever. It doesn't really matter. But there's a location closer to the 10 amp wire such that the magnetic field strength of the 10 amp wire is as strong as the magnetic field strength in the 15 amp wire, because if you're at the middle spot, like we did in Part A, the 15 amp wire beats the 10 amp wire for magnetic field strength simply because of the bigger current. But the further you get from the 15 amp wire, the field weakens, and the closer you get to the 10 amp wire, that field strengthens. So at this location right here that we're looking for, let's call this distance X. If that's distance X, this here is 10 centimeters minus X. because we know that the whole distance between the two wires is 10 centimeters. Well, that's 0.10 meters. Let's do this in meters. So this distance is 0.10 minus x. All right, and at that location, I need to have B1, here's the condition, I'm using blue now, the magnetic field, or B10, the magnetic field strength of the 10 amp wire, which is towards the floor at that location, needs to be equal to in magnitude the magnetic field strength of the 15 amp wire, which is towards the ceiling. They just need to cancel. They both need to be like 18 Teslas. Towards the floor and towards the ceiling, they cancel. All right, so bottom line is B is mu 0 over 2 pi I, I'm going to call it I10, the current in a 10 amp wire, over R10, that's the distance from the 10 amp wire, equals, I haven't plugged anything in yet, you'll see some simplifications already, mu 0 over 2 pi current in the 15 amp wire divided by the distance from the 15 amp wire. Once again, we're not trying to find the force between the two wires, we're just trying to make the magnetic field strength from each individual wire equal to each other so they can cancel out. Well, what you can see here, speaking of canceling out, this will cancel out, this will cancel out. They're the same on both sides. There's no terms here, these are all factors. So if you plug in here, the given numbers now, or the values, I10, I sub 10, that's the 10 amp current. So plugging in, I'll stick with blue. So now this 10 represents 10 amps divided by how far am I from the 10 amp wire? I'm x, a distance of x. I've labeled that in my diagram. Equals current in the 15 amp wire, which is 15 amps, divided by how far am I from the 15 amp wire? I'm 0.10 minus x. Bottom line is now, all you gotta do is cross multiply to figure out what x is, and at that location, that's where the two magnetic fields would cancel out. And as a matter of fact, it's not too hard to figure that out. That would be true anywhere now along, if I'm going back to the diagram, along this dashed line. So that's the entire location. All points along that blue dashed line is where the magnetic field would cancel out. Anywhere to the right of that blue dashed line I just put on the diagram, this line right here, anywhere to the right of that, the field from the 15 amp wire dominates, and it will be towards the ceiling anywhere in this region, because that dominates over the, because that's what's going to be on the left hand side of that wire. Over here it's going to be towards the floor for both wires. If you go that far away from the 10 amp wire, it's towards the floor, and for the 15 amp wire it's towards the floor. So everything over here would be additive towards the floor. This would be towards the ceiling, because the ceiling magnetic force field is stronger for the 15 amp wire than for the 10 amp wire towards the floor. Here the 10 amp wire dominates because you're a little bit closer to that wire, and that one's toward the floor net. And then to the left of this wire, if you were to ask, I'm just giving you all the extra things if you were asked for these, this would be on the left hand side of this wire. For the 10 amp wire, that would be towards the ceiling, but it would also be towards the ceiling for the 15 amp wire, so you would have a net magnetic field towards the ceiling everywhere towards the left hand side of this particular wire. But here's the only spot where that would cancel. You get a net zero magnetic field, but only in the plane of this paper. All of what I'm talking about is in the plane of the paper, where it's easy to add and subtract the vectors that are either straight down towards the floor combined with something straight up towards the ceiling, which is easy addition or subtraction with no components.